Chapter
I can
16.
get you while you're eating. Everybody knows that.
It's so stupid.
I got yelled at in a plane because everybody else was drinking.
The first section of chapter 16 deals with definitions. I will remind you that in chapter 16 we introduced all of the different acid-base definitions. We talked about Arrhenius. We talked about Bronsted-Lowry. And we talked about Lewis. Please make sure you know those definitions. But the most important, in my opinion, is that of the Bronsted-Lowry. It says acids are proton donors, and bases are proton acceptors. We talked about the terms acid, base, conjugate acid, and conjugate base. Remember that water is amphiprotic. Acid base, conjugate acid, conjugate base. What else? The hydronium ion. Is a Bronsted-Lowry concept. A lot of times, and I will remind you of this now, we use the two proton hydronium ion interchangeably. They mean essentially the same thing to us. One of them is the same as the other as far as shorthand. The autoionization of water. So this was actually the autoionization of water was the KW. AKA when water splits into positive and negative, we get this. Remember that for pure water at 25 degrees Celsius, this is 1 times 10 to the negative 14th, which then, of course, sets the stage for the pH scale. Okay, the pH scale says low numbers are acids, high numbers are bases. It is calculated using a formula. Concentration of the proton, take the negative log of it, get pH. Again, runs on a scale of 14 because of the autoionization concept for water. Here's where we also introduced that if you add pH plus POH, you get 14. That, ma'am?
Mrs. Valent is wondering if she could borrow a box of tissues.
Right there. That's like the third time, right?
Oh,
Oh, on the cart. Look down.
Oh, awesome. Thank you.
Guess a lot of kids are sick. Oh. Allergies?
It's allergies.
I take an allergy pill every night.
Yeah, I took an
Works really well. Every night. Part of my daily routine now.
I've just been taking.
Probably until sometime in July.
Yeah, I use Benadryl.
After I get done running.
All right.
I have pneumonia.
So here we go. From there, we can also then say, how do we calculate POH? Correct. If we want to solve for a concentration given a pH, do you remember how to do that? right? We take 10 to then both sides and you get 10 to the negative pH. Same for OH. If I want to calculate the OH minus concentration, I get 10 to the negative POH. Okay. What does a strong acid or base do? Complete dissociation, or ionization, if you will. Whereas a weak acid or base, partial the common strong acids perchloric acid, hypochloric acid, oxy acids, HI and HBr. There are 7 of them. You are supposed to know them. Bases are going to be hydroxides of group 1 and 2 metals. Whatever. All right. From there, we introduced the dissociation constant, the acid dissociation equilibrium constant, Ka. That guy. Remember, you could also write it with an H plus instead of an H3O plus. Just remember that those two are interchangeable. Don't forget that. We also talked about Kb, the base dissociation constant, and then we related the two. This is one of the chapters we split into 2 on purpose. H3O plus. This one?
No, what's right next to it?
This one?
A?
A minus.
What does HA stand for?
Acid. So these are the general equations. So this is like a general dissociation of an acid. And then the general dissociation of a base was to take the base, add it to water. Sorry, I always like to write my H's first. So general base dissociation, general acid dissociation, strong, okay? This section also said, if you multiply the two, what do you get? Anybody remember? KW. If you multiply Ka times Kb, you get Kw, which is that 1.0 times 10 to the negative 14th. All right. Ooh. Yep.
Okay.
You'll be given the formulas you need.
No, I'm talking about the.
Kw values.
Did you just say
Yeah.
it was specific?
Yeah.
Okay.
That's a constant.
Okay.
You get constants and you get formulas.
Okay.
All right. Next up is polyprotic acids.
Yes.
If I have a polyprotic acid, multiple protons, right? This is the one I've got. And I remove one. I get this. And in order to do this, there's an equilibrium constant associated with it. And we call it Ka1 because it's the first proton. If I then take that conjugate base, add it to solution, try to remove another proton, there's another dissociation constant. And finally, if I take that last one, and I just chose one that had 3, but it could work for 2 or 4. We get that. According to what we've talked about, as you do this, the reaction gets more and more reactant favored. So what does that mean about K? Does it get smaller or bigger? Think about it. Small values mean reactant favored. So Ka1 should be the biggest of the Ks for a polyprotic acid. And they get progressively smaller in big numbers, right? So one might be 1 times 10 to the negative 6. The next one might be 1 times 10 to the negative 11, and so on and so forth. Okay, so a very big leap between them. So that's the rule for polyprotic acids. All right. I'm going to talk a little bit about a mean. I think it's 16.7, yeah. Is NH3 an acid or a base? It's a base, okay? But it's an odd base for us, okay? So we just need to make sure that we remember there's some odd acid-base chemistry that goes through this amine compound, okay? NH3 can act as a base. Could it theoretically act as an acid? Yes, because it has protons. Unfavorable, but I digress. Its conjugate acid is more acidic, right? It gains a proton. Now it has one to give away. It wants to give it away. That's really all I want to talk about with amine. It's one of the most commonly used as an example for a base equation because it's an odd one. It's one of the few bases we know of that doesn't have hydroxide that still behaves like a base should. That being said, the next thing we talk about is oxy acids and Lewis acids. Yeah, so 16.8 is this equation. And it's manipulate this equation. Okay? 16.9 talks a little bit about hydrolysis. What does that mean? We talked about that yesterday. When something is hydrated, what does it mean? Surrounded by water. Hydrolysis is a similar idea. We surround ions with water. Uh, 16.10 is a conversation on oxy acids. Remember, we just introduced a bunch of acids that had oxygen in them. They tend to be pretty strong. Pretty strong. And then 16.11 opens up the floor for all compounds. That's the Lewis acid and base theory. Is that everything is a Lewis acid or a Lewis base because everything is an electron pair donor or an electron pair acceptor.
Are those like the same thing as the Bronsted-Lowry?
No, not at all.
Okay.
This is the most generic definition for a Lewis for an acid or a base that we came across. I can only say that pretty much any and all compounds could fit into this definition if you try hard enough.
And I remember one of the questions on the quiz was like, which one?
Is a Bronsted-Lowry acid? Yeah. So there are some that you can say, which of the following is a Lewis acid but not a Bronsted-Lowry acid? And you're looking for electron pair donors and electron pair acceptors. That means draw Lewis structures. If you hear the term Lewis acid or base, draw Lewis structures and look for lone pairs. If it doesn't have lone pair, it's going to be a Lewis. It's going to be an acceptor, right? If it does have lone pairs, it's going to be a lone pair donor. On the center atom, remember, always look at the center atoms. Acids are going to be the acceptors. Bases are going to be the donors. Okay. All right. That was chapter 16. We did a couple of labs with this one. We did pH of household substances. Yes, ma'am.
Did you say lone pair was the acceptor or the donor?
Lone pairs are what you're looking for in the center atom. If it's an acceptor, what do we say? Acid. If it's a donor,
Well, how do you know if it's a donor or an acceptor?
if it has lone pairs,
So if it has
it's
lone-
got to be the donor.
Okay.
If it doesn't have lone pairs, it's got to be an acceptor on the center atom. Does that make sense?
Yeah.
But this is why we say the Lewis acid base definition is so useless. Well, useful, but it basically puts every compound out there into one of two categories. All right. That is all of that. All right, let's go on to chapter 17.
So donor is acid.
No, didn't we say acceptor is acid? Electron pair acceptor is acid. Electron pair donor is base.
If you think about it, with the Bronsted-Lowry.
Let's talk
because
about
the-
chapter 17.
The proton is given. You don't have to accept any other definition.
This is exhausting.
You remember, right? So for Bronsted-Lowry, either acids donate or accept. They accept the H plus.
Acids or bases?
Well,
Acids are
give
proton donors.
proton.
Bases are proton acceptors in the Bronsted-Lowry. In Arrhenius, acids are proton increasers, and bases are hydroxide increasers. They go general to specific. That's how they work. All right. Let's talk about chapter 17, aka more ice tables. Section 1. Oops, we're not in 14. We're in 17. The common ion effect. You all right back there? Think you're gonna survive or no? Probably not gonna survive here. Good talk. All right. Here we go. We start with a weak acid, which will dissociate into two things, the proton and the conjugate base. All right, so we are told that the common ion effect will shift equilibrium. Remember, this is all Le Chatelier's. These are applications of Le Chatelier's principle. It says if we mess with something, right? So let's say let's say this thing is at equilibrium already, and then we add more of this. What has to happen?
Has to shift to
It has to form more of this stuff to get back to equilibrium. Okay, so if I add something acidic, what happens? It's got to shift back, right? So that is what Le Chatelier says. So if we start, and we're going to talk ice tables again, right? Let's say that we are given information along the lines of, what is the pH? First off, how do I calculate pH? What do I need? I'm going to need H plus, right? That should be the first thing you look for when you're doing acid-base equations. is if I'm asked a pH, I'm going to need an equilibrium or I'm going to need a concentration of H plus at some point. Okay? What is the pH of a solution made by adding pH of a solution made by adding 0.30 moles of acetic acid to, and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. Okay, so first thing you have to recognize is you were given the acid concentration, right? You were given the acetic acid was 0.3 moles in 1 liter, so what's the molarity? 0.3 moles per liter. Yes, ma'am.
What does the part say after like NaCH, COO?
This one?
Yeah.
To enough water
Okay.
to make. Yeah, well. So we're told this. What else were we given? We were given this guy. All right, is that the CH3COOH?
Yeah.
It's in it.
It's got part of it, right?
Yeah.
It's got the ion. Technically, this, when you break it apart, will become this and this. So this is what? The common ion. So our initial concentration we were given goes here. Yes, ma'am.
So I struggle with when there's like H ions on the product side. So if there's 2 of them, how do you know which one to make the acid and which one to make the base?
Like 2 compounds that have protons?
Yeah.
Like, is that what you mean?
Mhm.
So
Because you want to turn that water into hydroxide, right?
this is where you're supposed to know that this is an acid part of the argument comes in, because water can be either the acid or the base.
Mhm.
Whatever this is determines what water will be.
Okay.
Okay? Now, again, other examples are things like this. You're supposed to know this is the base.
Okay.
Does that make sense?
Mhm.
That's the problem, is that you need to make sure you know that this thing must be the acid. Right now, in the case of something like this, if we added water, because technically there's always water, right? If we added water, this thing has to be the acid, because 1, it has the proton, and 2, this thing will not be the thing that determines the other.
Okay.
Water never will determine what the other thing is going to be. It's always the other way around.
Okay.
Always look at the thing that isn't water first,
Okay.
if that's the equation you have. Good question. Okay, so here we are. How much of the proton do we have to start with? None. What do we do next? How did I know to put the positives on the right and the negative on the left?
0.
Because of the 0. Nope, because of the 0. I can't subtract from 0. I can't do minus x here. I have to do plus x. Jeez, where's your mask? Dude. Yes.
So if the 0 was on the reactant side, then that side would be.
Then that side would be the positive, correct. Where the 0 is determines the positive negatives. All right. Here we go. Here's where we started ignoring x in our equilibrium expression. What goes on top? Remember, we can ignore x. Remember? Ignore. What were the rules for ignoring? They must be at least 3 orders of magnitude different, right?
They never happen.
We very rarely have ignored x and then have to go back and do a complete recalculation.
I don't think you've had us do that before.
Nope.
It's usually just kind of
Hint,
give it
hint.
Pretty much. Okay. We need the Ka for acetic acid. Dum dum dum. Which is 1.8 times 10 to the negative 5th. All right, what do we do next? Is that value in molarity?
Yes.
Did we put it in the table in molarity?
No.
We did.
Yes.
No one knows. No one actually knows.
What's up?
What happens if we ignore X at like the earlier one of these problems on accident?
It might not work out on you. I mean, I'm telling you that the reason we didn't ignore X until chapter 17 was because it would not have worked out for you before chapter 17.
You just tell me when to ignore X because I can't promise it.
I mean, I will probably give you a hint of, in these problems you can ignore the change in X. In these problems you cannot. If you choose to ignore X when I tell you not to, you'll probably get a 0 on that problem.
Oh, a 0.
Ignore X and I spent like 10
If you choose to ignore the directions, I'm going to go ahead and give you a 0.
Oh,
Yes? Say again?
So do you remember the last time I tried to ignore not ignore X and I like was almost crying at your dad?
I'll do my best to remember to tell you when to ignore X and when not to. But you do need to practice some of those quadratic formulas if you don't remember. All right, moving on. So this is my X value, which is in moles per liter. What do I do with it to get pH? Because that was my question, was what is the pH?
Plug it into X for.
We're going to plug X in for pH. And what do we get?
A number between 1 and 14.
4.74. He's his own dynamic duo.
Oh, okay. Zach.
Who is? Oh, Zach.
Zach, you're clever. I still think
It's
clever.
It's brilliant.
That was section 1. Moving on to buffers.
Dang it, you should have never done sandwiches. I would have
Yeah,
Well, these
seriously.
aren't open.
Yeah.
open them.
We have open ones at home. It's like you can't open a new cereal box until you finish the old one.
All right. What is a buffer? Yeah.
It is something that resists pH change.
It is a solution that resists large changes in pH.
What is?
Oh. What is?
Being made fun of.
I mean, I'm not the one who's taking fun.
That's true.
It's really gonna suck
Major stuff.
for us that aren't really ready.
Embrace the suck.
Don't ever say that.
The Henderson-Hasselbalch equation gives you a way of using Ka values and concentrations to determine the pH of a solution. In order to do this, you have to have concentrations of acids and bases, know which is which, and determine what the pKa is. How do you find the P of anything?
Negative.
You take the negative log.
That's the one thing I remember.
If we want Kb, we do the same thing, etc., etc. Next up is titrations.
She just breaks up pirouettes during the middle of our final. Okay, time to do a titration.
You miss it, you fail.
Instant
Lightest pinch
Fail.
you've ever seen. Lightest pinch you've ever seen.
Instant fail.
She got like a strip of
All right.
No, it's like enough.
Problem 815.
All I heard was
Wow.
Continue.
Don't ask me. I don't know.
Go.
Thank you. So nice. Oh no. Hold on, I'm gonna slosh some more. It's okay, I was gonna so
What does this even matter? What is pink? What is pink?
bad. No, all I heard was, ah! It smells good though. I'm sorry to get you.
Is that increasing in number before the jump up?
Hmm?
Is that more increasing or constant in already before it jumps up?
The difference between strong acid, strong base titration, and weak acid, strong base titration is where this, or what this looks like. So in a weak acid, strong base titration, which is the second of the two that we examined, this kind of went like this before it leveled off. Does that make sense?
So it is constant generally?
What?
The circle.
I wouldn't say constant, but I would say small changes until you get closer and closer to the equivalence point. Remember that there are 3 zones to any titration. There is pH before the equivalence point, there is pH at the equivalence point, and then there's pH after the equivalence point. This one's going to be a strong acid with a strong base. How do we know that it's a strong acid-base titration? Is because we start at low pHs, it stays about level. At some point it jumps up dramatically and levels off again, okay? How do we know that this is a weak acid? Again, we're looking for those 3 zones. The first zone is that small change in the weak acid. The second is going to be your equivalence point again. And the third is going to be leveled off once we've added more base than there was acid to begin with. All right. Quick note about equivalence points. If it's a strong acid base, the equivalence point should be a pH of 7. Exactly, yes?
Is there going to be a weak acid strong base on the final exam?
I mean, I can ask you either one of
Isn't
these.
the equation different for the...
For what?
For the weak acid strong base, isn't it different?
It's slightly different in the ice table. Is that what you're talking about? The ice table is slightly different, yes. We haven't gotten there yet. We're just talking about the titration curves first.
Oh.
That's where we're at right now.
So we haven't even done like the math come yet?
Nope,
No, that's
we haven't gotten there yet. Those are ice tables. Remember you did this as a take-home problem where you did a titration and you calculated pH at several points using the ice tables. Yes, ma'am.
Is the bottom one a weak acid?
Weak acid, strong base. Strong acid, strong base. Yes.
I think if you start with a base, it's opposite.
Right, so if we did a strong base titrated with a weak or a strong acid, we would flip it. So let's say that we used a strong acid instead of a strong base as the titration. We would start with your basically what she's asking is if we invert it, right? So this would be a strong acid with a strong base. I guess you would flip them, technically be a strong base with a strong acid, whatever. If we did the weak version, what would it look like? Like this, but inverted. So if we did a weak base with a strong acid, we would have a less straight curve do-do-do-do. right? So make sure you can understand how these work. Giving you a titration curve and saying, what is this, is a really good question, right? Is this a strong acid with a strong base? Is this a weak acid with a strong base? Is this a weak base with a strong acid? Is this a strong acid with a strong base? That makes sense? You will never do a titration with something that isn't strong on this axis. Whatever's on that axis should always be assumed to be a strong acid or base. Yes, ma'am?
So you know it's weak, so it goes down.
Right, so you're looking for a less level part of the initial curve if it's weak. Okay. All right, let's do some pH calculations. We're going to do strong acid base first. Can I erase this top stuff?
Sure. You're bored.
I mean, I kind of need it. I just don't want to erase my titration curves if you're still drawing them.
No, you're fine.
Okay. All right. Next up, calculations with titrations. I think I'm still in section 3.
Buffalo Bill. Bishop, are we gonna do this in 4 minutes?
Probably not. No.
Is that a challenge? You can do it.
I don't know if I can keep up.
We can.
Yeah, she's pretty fast, not gonna lie.
$49 mil. 51 mil. Molar. NaOH.
I used to know how to do these.
Added to $49 and $50. In other words, if we're ignoring the things that don't matter, like sodium, chloride, and salt, this is our net ionic equation. Okay? From there, we do an ice table. Write a K expression.
We don't ignore water in this, right?
No, we do. That's what our K comes out to be, right? Products over reactants. We always ignore water in our K expressions, always. That's how it is. All right. We need concentrations, right? Could we start with, so these are the types of tables where we used moles in the ice table. Then convert at end to molarity. So this is where we had to add our volumes at the end, divide by the total volume at the end after the titration point. We're going to do the 49 milliliters first. So in order to figure out how many moles are present, we're going to take the volume, we're going to multiply by the molarity, and we're going to get moles. For H, which is this guy, it doesn't change. All right, so that's our number of moles of H+. That number is going to be the same for the entire time. For the 49 milliliters, that comes out to be this. Technically, we start with nothing, right? Then we added this. Remember that with strong acid-base titrations, they completely react. So, that's going to go down to 0. That's going to go down to moles of H+. So we have H+ left over before the equivalence point. Does that make sense in what you're adding? You're adding 49 milliliters of base to 50 milliliters of acid. They're the same concentration. You should have acid left over. After, we'll have this guy left over, right? Okay, so here is my concentration, or I'm sorry, my moles. We have to get that into a concentration. My total volume after the titration is 99 milliliters, or 0.099 liters. Dividing that gets me 1 times 10 to the negative third molar. pH is the negative log of that number. pH is 3. So before the titration, and again, this is a strong acid base. Remember, we're doing this. We're about here. After the equivalence point, so after we add more than 50 milliliters, we should be about here, on the opposite side of the titration. Yes, ma'am?
Where did you get the 0.99?
That's the total volume of the titration. That's the 49 plus the 50.
Oh, okay.
We shall continue tomorrow. There are chapters I'm not going to get to. They're the later chapters. You're going to have to review on your own on some of them.